Welcome to this season on Graphene, which is, I don't know, every one of us has heard about the wonderful properties of graphene. It seems to resolve every problem in our lives. So we're here to understand better what it really can and cannot do. So let me introduce you Professor Walter Heer with the Georgia Institute of Technology, a well-known, recognized expert in this technology, and he's going to help us understand better what graphene can do and cannot do. Thank you very much, Professor.
Okay, thank you.
Time.
I think I'm going to have to, am I on here? Can you hear me? I have to be a little bit louder because I have to fight a big conference hall there. So you'll see the subtitle here. It's probably not what you expect. And actually, I should say, when I was invited to give this talk, I was a little surprised because I thought, who's my audience going to be? I'm a physicist, actually. And I've been working on graphene actually since the beginning, since the very, very beginning. In fact, before the beginning. And I'll explain how that works. But the reason it's not what you expect, because I think that the hype that has been involved in graphene is so extreme that it almost becomes a sociological problem. And I think it's about time that I'm going to test this on you guys. I want you to hear the truth. And the truth is not what you think it is. In fact, it took a long time for me to eke this out, and I'm in the middle of it. And so the bottom line of it, there's enormous amounts of money involved. There's enormous amounts of ego involved. Of course, there's a lot of industry involved. And so the story is complex. So I hope you will listen, and I hope you'll understand. I'm not here to, well, let's say I'm just here to tell you really the truth. So it's surprising. So let's get started. Am I supposed to click my way through this, or you? Okay. So why did graphene start at all? Let me make sure I do this correct. It actually started because of this, because of the silicon revolution. And as many people know, do I have to yell, or am I overdoing this here? Can you put my, I feel I have to yell. Okay, fine. The point is this, as we all are enjoying our laptops and our iPhones and all that, it's purely and only because of one thing. It's because of silicon. And silicon has been increasing and has started off really, really small in the 1970s. And at that time, there were only a few transistors on a whole chip. Well, coming up right now, that's gone up by about 6 orders of magnitude, a factor of 1 million or more. It's billions of transistors are now on a single silicon chip. And the way this increases is exponential, and it keeps going. It doubles every 1.5 years. The performance doubles, but ultimately this has to end. And this is called the red brick wall, or the end of Moore's law. That's how it's called, and that means suddenly you can't do it anymore. And you really, in a couple of years, don't expect to go to the store and get a better cell phone or computer. It stops. Now, this is a big fear of industry. What happens if suddenly we can't buy a better computer every 1.5 years? It's a big, big problem for industry. When that stops, there's a big part of the electronics industry in the United States that's going to suffer very badly. Intel and all the other bigger companies. China is going to do very well, by the way, because they'll continue manufacturing, but the innovation will be gone. So this big fear has driven a lot of effort to revolutionize electronics with new materials. This has been going on for 20 years now. So then comes graphene. Now, graphene came along around the end of the 1990s because of another revolution, so-called the carbon nanotube revolution, where people found that carbon nanotubes, and if you never heard about it, it doesn't matter, could make good transistors. Well, I came out of that group who finally figured out that maybe the origin, what made graphene nanotubes so good, was actually the thing called graphene. And graphene is actually a single layer of carbon atoms. And this is straight from Wikipedia. Graphene is a single layer of graphite. Now, if you buy some graphite, you will find it's a three-dimensional material. It's just a material. It's like a pencil lead, but it actually consists of these kinds of sheets. Now, how long was that known? About 200 years. It was in the 1850s and 1860s. There was a chemist called Atchison who was the first one who actually figured out that graphene consisted of these carbon layers, and he was able to actually exfoliate it and make suspensions of this material. And, but nobody had any use for that. A few did. But in any case, so graphene is a pure carbon in the form of a very thin, nearly transparent sheet, 1 atom thick, known for long time. While scientists had theorized about graphene for decades, out of Wikipedia, it was first produced in the lab in 2004. That's completely false. There's absolutely no reason to even believe this is true. And then comes, but this is a part of the story that makes a new revolutionary material. Well, it certainly has to have a discovery. Well, here is actually where the discovery is announced, by the way. Everybody refers to this paper as the original first paper in graphene. Now let's look at the very first sentence of the abstract. Monocrystalline graphitic films which are a few atoms thick. This is not graphene. This is the ground foundation. It starts here already. Graphene films were a few atoms thick. This paper is not about graphene. It's about thin graphite. Absolutely true. This is the actual first paper. Now, I'm not going to overload you with a lot of physics, and I was actually told don't show the electronic structure of graphene, but it turns out that graphene and graphite are very, very close in their electronic structure. This is the band structure, so-called, of graphite, and here's of graphene, and only really right over here in a very small region of the space you see a small difference. They're very, very closely similar. But it's even worse. You've all heard that graphene is the best conductor in the world. You know what? Sheet by sheet, there's a better one. Guess what it is? Graphite. This is experiments done by Sewell in 1958, and he finds something called a mobility, and the mobility is about 10 to the 6. That's a very big number. It's about 50 times bigger than graphene. Graphite is actually, if you just do it the same way, apples for apples, a better conductor. That's known by physicists, by the way. How about this? It was first discovered in 2004. Up there is a picture by a German chemist who actually exfoliated and measured using electron microscope, one of the first measurements using electron microscope, isolating in 1962. That's graphene, right up there. Now, I talked with the man, and I said, well, why didn't you start a revolution? He says, nobody cared about this material. It had no purpose. More and more graphene pictures going 1962, 2002, 1999, all pre-2004. So what's going on here? Well, here it is. So this is pictures from The Wizard of Oz. I think you've all known about The Wizard of Oz. We got the wizard there proclaiming all kind of wonderful things, but in the background it's much more mundane. So why don't we know about the truth? Because many experts see... Now this is, by the way, when I tried to publish some of the story I'm telling you right now, I was actually sent it to Physics Today, and the editor said this. He didn't want to publish my article revealing a lot of this stuff, saying many experts see the hype in some papers, but they mostly recognize it, roll their eyes, and move on to the science that matters. Okay, now explain why this happens. Now, I'm not going to tell you that graphene is crap. I'm not going to. I spent a decade on this work, and I'll tell you what it's good for. But it's not, again, what you think. There were hundreds of papers by 2004 explicitly mentioning graphene in it. You can Google this. It was known experimentally in over 100 patents. 100 patents pre-2004 mentioned graphene explicitly. It was named in 1989 by the same guy who first discovered it, Hans Bohm. He actually named it. So I'm just setting it up a little bit. Its extreme stability, which was so-called a new invention, was known since the 1930s because it's just graphite. It had already been isolated in 1962, as I already told you. Okay, so what's the first lesson here? Many graphene applications are really graphite, sometimes involving little more than a name change. Now there's something else. Serious intellectual property rights for those who want to invest in this stuff may be involved down the line, and I will show you why. Because very often they have taken away the idea that graphene is a single layer and let multi-layers, which is now called multi-layer or few-layer graphene, suddenly has replaced single-layer graphene. So the very foundation, what makes graphene, graphene already has been shaded. So you're really not getting what you expect. And I know I'm not speaking with to a technical audience. And again, if I were talking with a technical audience, they would simply roll their eyes. Well, be careful here. So how is graphene sold? Well, right now, we have actually one of the participants. There's something called a €1 billion graphene flagship program. There is an industrial university collaboration in graphene in Europe that was awarded €1 billion. That is a lot of research money. And a lot of researchers like me really like money to do research. And it's very important to know that you know, people like me will eventually say, oh yeah, I'm working on graphene, and hold out their hand. That's the way it works. So let me show you how that was sold. This is a graphene information booth. This was a kind of a rolling circus that went around Europe trying to convince people to invest in graphene and to invest in this whole program because it was a competition, this $1 billion thing. And this is a graphene booth. And so it has stuff like this, and you can walk up to it. Here you can make your graphene with Scotch tape. I don't know if you know how you do this. You take a piece of graphite, you put tape on there, you peel it off, and little flakes of graphite come off, and that's graphene actually. Again, then you can actually investigate. You have a little microscope sitting there, and behind there is the future of graphene. It tells you what are future headlines of graphene going to be all about. So I actually lifted a couple of these out here. First of all, airplanes with wings made from graphene composites. Graphene composites are materials made of this brand new, never known before material. It's going to be extremely strong. And these were fake headlines. Some simply say, imagine you will see this one day in 2020 and other days. Fake headlines. Flexible matter. Graphene is flexible and ultra-conducting material. Well, graphene-based plastic electronics. Transistors that go beyond the terahertz. This is an extremely high frequency. Chemical fuel cells revolutionized by graphene. Credit card, mobile phone. I mean, you can go on and on. This is literally how it was sold. None of this is true. None of this has any basis in any fact. There's nothing, no research, nothing to support any of this. But how can you get away with all of that? Well, these are pictures that I lifted off of this website, actually dropped off the bottom. But transparent conductors, this is all, again, selling graphene, flexible electronic displays, super-sensitive medical sensors, explosive detection, stronger, lighter, safer transport, green cars, cheaper solar power, artificial retinas, artificial whatever, ultra-fast computing. So what is this? If I look at it, what can we actually believe in? Transparent conductors, yes. That is absolutely true. Because why? This stuff is so thin you can see through it, and because graphite conducts, it conducts. And so there's use for transparent conductors, by the way. Flexible electronic displays, unlikely to be competitive, and I'll show you why. Super sensitive medical sensors, again, unlikely to be competitive. Explosive detection, no. Stronger lasers, transport, no. Green cars, no. Cheaper solar power, no. Because there's no scientific evidence for any of this. artificial resonance, and ultra-fast computing. And here I'm going to hedge my bets. This is something that might happen, but not tomorrow. So again, now here's a roadmap for graphene, and I'm going to be quite short on this. And I want you to know that the whole graphene revolution started with the idea that we can develop new electronics, Moore's law. That was what it's all about. But quickly it transitioned to everything else. So how did that happen? First, you invent this material, discovered with this amazing electronic properties. It's going to revolutionize electronics. And within a few years, it's not talking about revolution electronics, but everything else. Now, to my mind, what this is a snake oil salesman. The little bottle that cures one disease, and when it doesn't cure one disease, suddenly it cures another disease. Beware when this happens. This is not a good thing. So in any case, in the graphene flagship program, what you'll see that they have moved away from the high-frequency special electronics stuff and gone to other things, touch screens, rollable e-paper, foldable OLEDs, whatever. I'll tell you what they are, but that's what they did. So they moved the whole, what it was originally supposed to do, they moved that into the future beyond the lifetime of this big program. I think that was okay, so I'm not going to talk about that. Now, some very important properties that I think right now you're getting the drift of this, that you should know. Graphite is stacked graphene composed of AB stacked graphene sheets. It was known a long time. Graphite ranks amongst the most stable materials known since the 1930s. The interlayer interaction ranked among the weakest. That's also known. And here, this is the important one. Essentially, all chemical, mechanical, and electronic properties of graphene are identical to graphite. Now, I showed you already the foundation paper, the one that ascribed graphene, that the starting paper in 2004 was not about graphene. It was about thin graphite. When you put 10 layers of graphene on top of each other, it's no longer graphene. It is graphite in all senses. So be careful. But let's go a little bit further with this. Okay, so yeah, this is actually, okay, since this is true, since essentially all chemical properties and all these properties are the same, therefore many applications of graphene have counterparts in graphite. And I'm going to show you how that works. And many of those have been known for decades, even centuries. This is scary. Graphite composites, graphite conducting inks, graphite lubricants. By the way, and all these things are now called graphene. So now I'm sure everybody knows the graphite tennis racket, the graphite golf club, all that graphite. Well, graphite's a fantastic material. It's extremely strong, and this is the material you can do many, many things with. Okay, it's important to realize that the name thin graphite has been replaced with graphene. If you now look in the literature, you'll very often see graphene mentioned when really graphite is meant. If you take 5 or 2 or more or 3 or 4 layers of graphene on top of each other, you have thin graphite. Chemically, technically, by any standards. So if it doesn't bother you, that's perfectly fine. But remember, you're not buying a new thing. You're not looking at a new thing. You're looking at a very old thing. Now let me show you how this works. Graphene is cashing on graphite by simply a name change. And so let me look at this quite carefully. Remember this flagship thing that talked about the graphene composites? That's going to change aviation. This is a stealth bomber. Guess what it's made of? Almost entirely graphite epoxy composites. So all you got to do if you want to make a new airplane out of graphene, you make the same thing and you change its name. That's all you got to do. And that's exactly what's happening, by the way. The composites that are now being designed around graphene are actually these composites. Next, lubricants. Graphite lubricants. What are these? These are really very, very fine graphitic flakes that have been put in a binder to make it look like something. And now we have the same thing now called graphene. Let's look at something else. Conducting graphite paint. Here, this is very interesting. And look, I hope you understand one thing. I'm giving you a very strong reality check here. This material is called Aquadag. Those in the electronics industry know what this was. This was a transparent conducting paint. It was a paint made out of a suspension of very, very fine graphite flakes. This was actually discovered by Atchison. Atchison was a chemist who actually first exfoliated graphite in 1850. His company, the Atchison Graphite Company, made this material. It has been used in the electronics industry ever since. If you analyze this material under the electron microscope, you'll find graphene flakes, so-called. Thin graphitic flakes, known, again, for a long, long time. So let's go some more. What about these applications? Can they actually stand up? Plastic organic exists. Look on the internet. Foldable OLEDs. This was one of the things that the flagship program was going to do. Well, here you see a foldable OLED. It's transparent. It's conducting. Happens to be made at Georgia Tech. I have nothing to do with this, by the way. But this is made with organic electronics. This is a big industry. Samsung and Sony and all that are going to make the new displays out of this stuff. Transparent conducting materials and OLEDs. Organic light-emitting diodes. Printable electronics. Transparent printable electronics. Also made by organic electronics. Rollable e-paper. It's already being made. It's made by different material, though. And finally, the flexible. Here, this is an OLED flexible display. No graphene in there. So this is what the graphene industry is trying to attack. These are mature industries. These are not new. So, fine. I'm going to skip through this a little bit more. The transparent conductors, which I believe actually has a chance of being realized with graphene. Well, this is also quite mature. There are many, many conducting, transparent conductors right now being made. It's a big industry. I don't want to go. Just look it up on Wikipedia. You don't have to go or on the internet a little bit more. And so I'm not going to go through this. Again, how to make graphene? Well, what people now do, there are methods to roll graphene between conducting sheets. I'm going to hurry up a little bit through this. This is the new technique where people are trying to make these transparent conductors out of graphene. Unfortunately, at the moment, it's not competitive. The resistances are still too high, and it can't compete against the standard material. Now, what is said, this is actually the roadmap for graphene. It was a recent article written by Novoselov and company. But basically, the bottom line here is what we really have to do is to make new electronic-grade graphene. The point about this, it is this. Right now, graphene is made by various techniques, and all are said to be very cheap and simple. For example, you take a piece of Scotch tape, you put it on graphite, you peel it off. That's a cheap way of doing it, and this is what the industry is betting on, that there will be cheaper and cheaper ways of making graphene. But there's something different between a cheap material and electronic-grade material, and this is where the rubber hits the road. Electronic-grade materials are very, very special, and I'll show you what they look like. I hopefully have that in the next slide. What's going to come up in a little bit. But you have to make, well, I'm going to skip through this because I know I'm going to be running out of time. So, a long time ago, when the whole story started, there were two papers actually that came out at the same time, more or less. One was the first paper that explained how you can use Scotch tape and all this kind of stuff to make graphene materials. And the other one was working in a entirely different fashion. It actually based their way of making graphene on known single crystal electronic semiconducting materials. That's the one I was working on at the time. No Scotch tape, working with electronic material called silicon carbide. And so I show you how that works. Epitaxial graphene is a material that you can grow by taking a silicon carbide crystal, and silicon carbide has recently got into the into your knowledge, because now you have these LED lights. If you go to Home Depot, you'll find these white lights. They are LEDs, actually, very, very bright and white. They're made out of silicon carbide. This is the same electronic material that if you treat it right, you can grow a graphene layer on it. Now, that process has been known for many, many years, and I'm going to go through it a little bit here. How do you do that? This was actually a method that we have been working with for quite some time, and it was copied from a method that was developed first in the 1970s. In the 1970s, people figured out if you took this silicon carbide, again, the same material that you get to see these LED lights in, if you heat it up, you grow a layer of graphene on top of it. Known very well. Silicon carbide is quite expensive, but the material you get out of it is extremely high quality. So this is a kind of graphene that we were banking on several years ago that could probably revolutionize electronics. This material, not the one made with Scotch tape, because the Scotch tape material is simply too dirty. So let's look a little bit more at silicon carbide as a foundation material for the graphene. Well, recently Raytheon has shown that this silicon carbide material is very good for electronics because you can heat it up to very high temperatures. Now, that's not maybe too interesting for your laptop, but for many applications, people care to have electronics that can be raised to high temperatures. For example, electronics in cars, electronics in your engine. If you want to have something monitoring what's happening inside your engine, the temperature has to be, and it should be able to exceed the higher, to well above 100 centigrade, and then silicon starts to fall apart. So this material can handle the high temperatures. So here are some very simple devices that you can make out of graphene on silicon carbide. So you grow the graphene on the silicon carbide, and you actually can make transistors out of it. What the problem with this kind of graphene is, it's pretty expensive. So, for example, a chip of silicon carbide to make such a kind of transistor, it's about $20 per square centimeter. Now, $20 per square centimeter is quite expensive. But, you know, that's the price you have to pay to get high-quality material. This is not the kind of material that you can make airplanes out of. This is the kind of material that can only make very high-performance electronics out of. Because at such a price, you know, you better want to get quality. So I was just warned that my time is getting quite short, so I'm just going to move through a little bit of these technical slides. And one of the biggest advantages of this material is that we can make structures of this kind. In fact, this is the very first graphene patent that shows you all kinds of electronic devices that you can make with this epitaxial graphene that are impossible to do if you don't have the graphene of the high quality as you would want it. Again, I'm going to move through this a little bit quicker. But I guess maybe this is the key slide I want to show you, because this, I think everybody can understand. The silicon industry has invested enormous amounts of money to make single crystal silicon. This is silicon crystal. It's a single crystal. That means every atom is perfectly well in its place. Why did they do that? IBM does this, or no, Intel does this, because if you use this as a foundation for your materials, where you know every atom is, you can basically make transistors that are as small as nanometers, extremely small, and you can make them reliably. Now, if you have a crystalline material, you can make very, very perfect electronics like Intel has been doing for many years. If you use this on silicon carbide is exactly like silicon. It's a single crystal. So again, you have this great advantage that the material is perfectly well defined, and because of that, you can make perfect nanostructures. Well, electronics requires nanostructures. So the long story short is there's no shortcut. There's no cheap way. If you want to make high-quality electronics, and that's what I think the only ultimate result of all this graphene stuff is going to be about, if you want to make high-performance electronics, you must have a single crystal substrate, and that's the way you have to do this. Okay, I'm being warned that I have to run through this. We have various techniques of doing this. Here, for example, are a couple of these graphene transistors that we now make. Here you see a graphene layer, very small, sitting on top of a silicon carbide. Every atom is in place, and we can make these by the dozens. Here you see, for example, a chip with 1,000 graphene transistors on it. Now, this is not cheap, or maybe it's even more. It's 10,000 transistors that you can put on a single chip of silicon carbide. This cannot be replicated or done with any other way, but it's expensive. You don't buy this. This technology is quite expensive, but it's real graphene. Now, I'm going to race through this because of time, and this is a new result of ours, that we basically were able to get the graphene conductances to almost to the superconducting levels. I'm not going to bother you with all of that. Let me just go through this a little bit more. And the final thing that we're doing right now is learning how to take our silicon carbide with the graphene grown on top of it and make integrated structures of this kind. Well, I'm going to now stop here. I don't want to make this a promotion for myself, but the basic point about it is that graphene, when you see graphene being used as building materials for all kinds of properties, you might actually be looking at graphite. In most cases, it is graphite. Graphene, by definition, is a single layer of graphite. And as soon as there's 2, 3, 4, or more, it's graphite. It falls under the category of graphite. The technology falls under graphite. And if people want to call it graphene, it's a name change. And for those people invested in this, watch out. Graphite technology has been around for many, many years. And I can bet you there are patents out there that override whatever patent you're going to try to do. We ourselves are betting very much on these new forms of graphene grown on single crystal silicon carbide, that they might have a chance. But don't hold your breath. If this happens in 15 years, then we're doing good. Okay, I'll leave it with that. I hope this message wasn't too negative, and I hope you got something out of it. Thank you.
Thank you really very much. This has been awesome. I would have 1,000 questions, but okay, in case anyone in the audience have questions, I will give priority to those of you.
Thank you for the talk. I kind of like exposing snake oil, so I enjoyed that quite a bit. You failed to mention my favorite application of graphene, which is I've got a little cube of graphene on my desk, and it's sitting on an array of 4 magnets, and it floats above, which is just so amazingly cool.
That's true.
I mean,
but you know what you're looking at? That is a property. It's a diamagnetism of graphite. You don't have graphene there. You have graphite.
I know.
Yes. Okay, it's a diamagnetism. Now, in fact...
but I couldn't get graphite to really do that now.
Yeah, if somebody says that graphite's amazing, if you can see it and hold it in your hand, it's not graphene, it's graphite. Yeah. So this property, this so-called diamagnetism of graphite, is a very well-known and I've seen these toys around for it too. It's fun. You get very pure graphite, you take some magnets, and it will literally float on top of it. The mechanism's actually not well understood. And it's not superconductivity, by the way. It's something else.
So, by the way, I am a member of the flagship European initiative. So I am ashamed now. But let's go to the next question.
Actually, it's not a question.
Can you speak up?
Just a little history here. My brother Richard Simcoe actually worked at Intel #1 with Mr. Moore.
With Mr.
Moore Theory. Actually worked alongside him.
I'm sorry, I missed a comment. Can you...
My brother Richard worked with Moore.
Oh, with Moore, yeah, okay. He's
Yeah.
still around, by the way.
Mm-hmm.
He's Gordon and Betty, so they're still around.
He founded Zycor ISDI,
Yes,
and he
yes.
was the inventor of the double EEPROM.
Brilliant guy, yes. Founded Intel eventually, and all that.
All right.
But yeah, it's and so he's very aware. I mean, obviously he is. Intel's very aware of this this impending doom, that really in 10 years can happen. Intel can really have fall into a major depression when innovation stops. And hopefully there will be something in that time to replace it. And who knows, maybe graphene will do something there, but it's not a sure bet.
So any more questions? So, okay, let's go there.
So you had on your slide graphene's not good as a cheap solar panel.
No.
Is it good for any kind of solar usage?
Well, the closest thing people can think about it is using as a transparent conductor of solar panels. So solar panels, you need to get the light in and through it. And if you can get it through a transparent conductor, that's really good. The trouble with graphene is a pretty good conductor, but really not such a good conductor when you make it 1 atom thick. 1 atom thick has quite high resistances. And so, yeah. But using it as a solar cell itself, there has been some talk about it, but the charge separation that you need hasn't been demonstrated yet. But you had a question. You had 1,000 questions. Okay.
Well, one at least. But if anyone more, well, I would like, I mean, this is a coil winding exhibition. So I think many of us in this industry, I don't know if all of us, but I have been definitely offered to coat the copper windings with graphene, for example, and then to amazingly increase.
Let me give you an interesting story here. Atchison, who made this conducting paint, this that I showed you, also demonstrated in 1901 that if you take his solution and dipped copper in it, it wouldn't rust. Guess what? This rust-preventing property of graphite suspension was known in 1901. It's amazing. If you want to have the references, I can show you. So graphite suspensions have the same thing. This anti-corrosion effect was known since 1901 of graphite suspensions, aquadag.
But eventually you would get a better conduction in the graphite or graphene coating, and then the copper would be just a mechanical withstand thing?
Yes, but again, look in the literature under graphite or aquadag or graphite suspensions and corrosion protection. It is a corrosion protecting thing. You can dip it in there and copper won't rust, iron won't rust. But this was known. And graphene doesn't add. Having 1 layer or 10 layers makes it just as protective, by the way.
Okay. So any more questions? If not, I would really say thank you very much. It's been really a great talk. Thank you very much.